One thing I like about solar energy is that it is virtually limitless. I also like the fact that it does not produce any waste or pollution.
This is how I show my love. I'm made in my mind because I'm blaming on my ADD, baby.
So one of the things that interests me about solar energy is the dual nature of light. On one hand, you have light as a particle, on the other it's a wave. It really kind of blows your mind when you start to think about it. It's a good thing we had scientists like Einstein, de Broglie, J.J. Thomson to figure this stuff out so we can better reap the benefits of solar energy.
What I found to be mind-blowing is the fact how subatomic particles have such an influence in our daily lives. An example would be how electrons are excited in metals when light hits it and emits the same image.
What is energy?
Energy is the ability to do work, the ability to cause motion and change. To understand the fundamental facts of energy, you must have a working knowledge of its terminology. From atoms down to X-rays, sing along and learn with me the ABCs and XYZs of energy.
What kinds of energy are there?
There's nuclear, mechanical, and solar energy, and electrical, and chemical, and radiant, and heat. There's light and there's magnetic, and that's quite enough for me, 'cause that makes 9 different kinds of energy. With the discovery of atomic energy, scientists have found that matter can be changed into energy, and energy can be changed into matter. But even though matter and energy may change their forms, the total amount in the universe remains the same. The law of conservation, speaking universally, says you can't increase or decrease the amount of energy. Though energy may change its form and does it constantly, you can't increase or decrease the quantity.
Now that we know a little bit more about energy, let's take a look at power and how it's created. Power, as here defined plainly by Wikipedia, is the rate at which energy is transferred, used, or transformed. The unit of power is the joule per second, also known as the watt, named in honor of James Watt, the 18th century Scotsman who invented the steam engine. But in order to power anything electrically, an electrical potential and current need to be created. So the question still remains, how can we take solar energy and convert it into an electric current to power things which require a certain amount of watts, such as this light bulb here? Well, believe it or not, it can be done just like that. Let's have a look at one of the methods.
Okay, take the natural heat from the sun, reflect it against a mirror, focus all of that heat on one area, send it through a power system, and you've got a renewable way of making electricity. It's called concentrating solar power, or CSP. Now, there are many types of CSP technologies: towers, dishes, linear mirrors, and troughs. Okay, have a look at this parabolic trough system. Parabolic troughs are large mirrors shaped like a giant U. These troughs are connected together in long lines and will track the sun throughout the day. When the sun's heat is reflected off the mirror, the curved shape sends most of that reflected heat onto a receiver. The receiver tube is filled with a fluid. It could be oil, molten salt, something that holds the heat well. Basically, this super hot liquid heats water in this thing called a heat exchanger, and the water turns to steam. Now the steam is sent off to a turbine, and from there, it's business as usual inside a power plant. A steam turbine spins a generator, and the generator makes electricity. Once the fluid transfers its heat, it's recycled and used over and over. And the steam is also cooled, condensed, and recycled again and again. One big advantage of these trough systems is that the heated fluid can be stored and used later to keep making electricity when the sun isn't shining. Sunny skies and hot temperatures make the southwest U.S. an ideal place for these kinds of power plants. Many concentrated solar power plants could be built within the next several years. And a single plant can generate 250 megawatts or more, which is enough to power about 90,000 homes. That's a lot of electricity to meet America's power needs.
Take a look at Spain's recent innovation to CSP. Over 630 mirrors, called heliostats, reposition themselves throughout the day to reflect the sun's rays onto two towers to create steam, one 50 stories and the other 35 stories. The heliostats are able to create temperatures of over 500 degrees Fahrenheit. Now those are some hot sunglasses.
Solar 101. How solar panels work. Commonly known as solar panels, photovoltaic modules are used to generate electricity. Solar panels are made from photovoltaic cells. Photo meaning light and voltaic, the production of electricity. Photovoltaic cells have two layers of semiconductors. Similar to a battery, one layer is negatively charged while the other positive. These layers are protected by two outer shields made from special glass. The semiconductor absorbs photons, or the radiation from the sun, and transforms it into direct current electricity, also known as DC. DC current flows to the inverter, which transforms the power into alternating current, or AC. This process takes place billions of times per second and is noise-free. The power flowing through the inverter is piped through a bidirectional electric meter into the main panel, which distributes the electricity throughout the house. The bidirectional meter displays net power used minus net power produced. When the solar system generates more electricity than you use, the meter spins backwards. What happens at night? The excess electricity generated during the day is fed back to the main panel. It's that simple. Solar panels have a life expectancy of 30 to 40 years. On average, utility costs rise by 6.7% annually. That means a $150 electric bill today will probably be around $720 in 25 years. Allow the sun to be your source of energy.
You are my sunshine, my only sunshine. You make me happy.
Solar energy is the most abundant and cleanest energy source the Earth has at its disposal. Solar energy, along with wind and biomass energy, has captured the attention as an alternative to fossil fuels such as petroleum and natural gas for energy needs. The rising cost of gasoline, along with the concern for the environment, has many countries focusing their resources on this alternative source of energy. Solar energy is also referred to as renewable energy because it is limitless and practically free. There is only an upfront cost that goes into putting the system together to capture the energy from the sun for practical use.
And no one could come between.
It would only take around 0.3% of the world's land area to supply all of our electricity needs via solar energy.
All of my dreams. You are my sunshine.
$83,000. That's the amount that one Air Force base in Nevada saves per month after installing a solar energy array on site.
Never know, dear, how much I love you. Please don't take my sunshine away.
If the world could convert entirely to solar energy for its fuel and energy consumption, it would save 90% of today's world pollutions. Alright, so we've built all of our circuits so far. We have one with 2 solar panels, one with 4, one with 6, we're going to test each one of them out individually and compare the results. So here's the 2 solar panels. As you can see, there's a little light. Alright, this is the second setup of our series. This is the 4 solar panel. Alright, this is our last one. It's got 6 solar panels, so it's the most of all 3, the ones that we're trying. So it should produce the most amount of light.
We all know that light bends when it travels through glass, water, or other transparent material. That's how a microscope, lighthouse, and spectacles all work. And you might even know that light bends because it travels slower through glass or water than through air. But why does light slow down? And how does it speed up again when it comes out on the other side? There's nothing there to give it a push. Well, if you think light is a wave, it's easy to explain. Electromagnetic waves simply travel slower through glass than through air. So the wave crests are closer to each other, but the light still oscillates the same number of times per second. It stays the same color. When the wave hits the air again, its color still doesn't change, while the crests spread out and it returns to light speed. The simplified explanation is that the energy of a wave is determined by its frequency or color, which doesn't change. So it doesn't need a boost to speed up at the other side. But wait, you say, I thought light traveled at the same speed in every reference frame. You still haven't explained how it can slow down. Well, now let's think about light as a particle. When light goes through glass, it gets knocked around and bumps into all sorts of molecules and electrons. So whenever it's traveling at the speed of light. But it's busy interacting with and scattering off lots of stuff along the way, and it doesn't necessarily take the shortest path through the glass. It's like the President of the United States trying to cross a room. If the room is empty, he can walk across directly. But if the room is full of people, all of whom want to shake the President's hand, even though he walks from person to person at full presidential speed, he'll get slowed down along the way. As soon as he reaches the far side of the room, though, he's free to resume his pace. Full speed ahead, Mr. President.
What are electromagnetic waves? Electromagnetic energy is a term used to define all the different kinds of energies released into space by a star. An example would be our sun. We know some of these energies as radio waves, infrared, visible light, ultraviolet light, X-rays, and gamma rays.
And coming up only to show you wrong. To the outside, the dead leaves, they are alive. For they die.
Make sure you zoom in on his mic.
Really?
Okay, mic is gone.
Please don't take my sunshine away.